All right, so our next speaker is Dr. Scott Glenn. Dr. Glenn's from Rutgers University and is also a member of the Mid-Atlantic Coastal Ocean Observing System, or MARACOOS Regional Association. Dr. Glenn, are you on the line?
Yep, I'm ready. Thank you.
Great. Hello.
Okay, I'll just start. There's our contributing scientists for the Mid-Atlantic, a bunch of people at Rutgers, including many students over the years. Doug Wilson at Okovi, Yi Zhu in China, and Hak-Soo Lim in Korea. Our overall goal up there in the corner, is improving understanding and forecasting of what we're calling these essential ocean features and the essential ocean processes that are responsible for the rapid coevolution that we see of the atmosphere and the ocean in these intense typhoons and hurricanes. That was a subject of my talk at the HFIP a couple of days ago. Oh, next slide. And so we've seen this already. There's the census of ocean features. These essential ocean features are responsible for impacting the hurricane intensity. We're still collecting this census. This is all based on the research during these response to the hurricane glider activities since Hurricane Sandy. And I like to draw the contrast between Catherine Edwards' area in the South Atlantic, where she looks at the Gulf Stream and the shelf and the horizontal gradients and how those features impact the hurricane intensity, and us in the Mid-Atlantic, right, where it's the vertical features, the surface stratification and the subsurface cold pool. These are the essential ocean features in our region that we care about. Next slide, Ben. And so here's a picture of that cold pool. You see it moving in the ROMS model down there in the bottom right. But in the wintertime, the water is the same temperature, very cold, top to bottom, unstratified in the Mid-Atlantic Bight. And as the summer comes along, the sun heats up the surface and this intense layer of stratification kicks in. We have a 10 to 15 meter layer of very warm water, a very sharp thermocline, and then cold 8-degree water below that. You can't see that from space, so you have to fly the gliders and zigzags back and forth across it, and then you assimilate that data into the models, and you can then forecast where that's going to be. Next slide. So having that observing system running for about 10 years in the Mid-Atlantic Bight, we've experienced several hurricanes, and we've learned a lot about the essential ocean processes that occur during the hurricanes. And these are the things that we've identified for those processes. First, we have the Irene-class hurricanes that go up our coast, right along the coast, and rapidly transit through the area. We've had about a dozen of these in the last 20, 30 years. They're characterized by this rapid onset of cross-shore winds, all those winds blowing towards the coast, piling up water from the surface layer, that pressure gradient forcing the offshore flow in the bottom layer. The shear-induced mixing between those two layers cools the surface layer ahead of the eye. And that rapid, intense cooling weakens the storm intensity and reduces the storm surge. The second class of hurricanes we have is the Sandy class. These are more slowly moving, they're more offshore, and as a result, you have steady alongshore winds that last for several days. And because there's that time to evolve, we get classic Ekman downwelling, where that cold water in the bottom is advected all the way offshore, sometimes all the way off the shelf, right? So it's gone. You have a warm layer filling the water column. And as the hurricane comes in, it can mix that warm water all at once. It's going to stay warm. There's going to be no surface cooling, no ocean-induced weakening, and no storm surge reduction. And so that's a very dangerous type of storms where we're not getting the protection that we see from the Mid-Atlantic cold pool from the Irene-class storms. All right, the next slide, Ben. All right, so we saw those essential ocean features and processes in our own research models and our own operational models for MARACOOS, but those aren't the ones that we use for hurricane forecasting. These are the models that we use for hurricane forecasting, and this is that operational workflow. It all starts with the Global Ocean Forecast System, GOFS. We're up to 3.1 now, and that ENCODA data assimilation scheme that pops the data in there once a day for each forecast. You see those incremental insertion windows there. The second line there is the NOAA sampling of that global Navy forecast. If you're sitting there on day 0, the model backs up 2 days, pulls that field as the initial condition, and then moves forward with NOAA winds through the area. And then we come down to the third layer where the hurricane forecasting occurs, where the RTOFs is subsampled and harvested, every 6 hours, and coupled to the operational or experimental HMOD and HWRF models. And then at the very bottom there is the operational HWRF that's initialized by climatology. That was probably 2019 is the last we'll see of that, I believe. Okay, so the next slide, we want to show how these how the glider data looks in these models. We started this process. Here's one of our very early deployments in 2016 as the Tempest project, where we had the glider going cross-shelf, seeing those 2 layers in the mid-Atlantic bight. We thought if we got this data to the Navy, it would be assimilated and that whole data flow would work quite nicely. This was back in the old days when we had GOFS 3.0. This was before 3.1 was available to us, had less resolution than 3.1. And as you can see, the ocean models, the global models in this case that are the start of our hurricane forecasting, there's no cold pool. The essential ocean features aren't there. We could hit it with that glider data all day. The model just rejected the data. It was too far from what the model truth was. And so it didn't matter. And so this is where we worked a lot with Pat Hogan at NRL then to continue to examine GOFS as it was transitioned to GOFS 3.1. And then the next slide will show you what GOFS 3.1 looks like. Here's the 2019 hurricane season, the many different glider flights that were on our shelf in that region. Just one section that goes along that white arrow up in the inflow part in the northern part of the mid-Atlantic, where you can see the sections of glider data, depth versus time, in the very first one, and you can see that cold pool feature very clearly in there. Then one below that is our Doppio for the MARACOOS region. This is a 4D VAR assimilation, very good assimilation for the region. It's been running there for many years, and you can see there's the very nicely defined cold pool and the thermocline. And there in the GOFS 3.1 model, which is a 3D VAR assimilation, you see that a global model is able to represent that cold pool on our shelf. And we think that's a pretty awesome development to have that there and to be able to modify that with the assimilation. It seems to be a very good start. And that quality of that data is retained as it goes into the RTOFs. As you can see that it's maybe losing some of it as it gets farther and farther away from the data assimilation, but we have a very good starting point. And so let's move on to the next part. Those glider tracks that you saw on the previous page, they're out there, but they're not, they're moving along those glider tracks, so they're not all out there at the same time. And so when you have that glider data in one spot, one of the first questions you ask yourself is how can you expand it to a larger area than just where the glider is itself? And one of the advantages we have in the Mid-Atlantic is we have this nice regional scale HF radar network due to MARACOOS. And back in the 1970s, about 50 years ago, Pollard and Millard had this idea for a model where if they blew the wind over it and they knew the mixed layer depth, they could predict what the inertial waves look like, what the inertial wave velocities are. Well, with the regional HF radar network, we're measuring the inertial wave velocities. We can pull those out. We can filter them out. We can get those every hour. And we have the winds every hour. Can we invert that model and predict what the mixed layer depth is? And that's the figure down below. The color temperature data is a time series of glider data during Irene that shows that central ocean process we talked about, the rapid ahead of eye cooling, as you start with the 2-layer system over on the right and move to the rapid deepening and cooling of that, deepening the mixed layer and cooling of the surface layer, all ahead of the dashed line. That's where the eye passages is. And if you look at that dotted black line, that's the Irene mixed layer depth as it evolves during the rapid forcing section of this storm. If you then take the MARACOOS HF radar and the NAR winds and the SLIM model, this slab inertial model, and predict what the mixed layer depth is, you result in that white line, and you see that it tracks very nicely the evolution of the mixed layer depth ahead of I and after the I. And if we can do that at one spot, and we have the HF radar data over the whole network, we can probably do it over the whole mid-Atlantic. And that's the next slide, please. Here we have 4 slides showing the progression of Hurricane Irene up through the mid-Atlantic. First, there's the very shallow mixed layer depth, about 5 to 10 meters over much of the area before the hurricane hits. And as it comes in, you can see the whole mid-Atlantic well ahead of the eye, the deepening of the thermocline as it progresses up through the region. And so this new piece of data, we're not even assimilating that yet. And so this is a new assimilation data set that we want to do. We're assimilating the surface currents, and now we can assimilate the depth of that surface layer along with the sea surface temperatures and the glider data. But what is causing that mixing? We wanted to look at more details of that. So the next slide, this shows the LES simulations that we've been doing of the mixing during Hurricane Irene. And when we look at the LES, there's 2 types of instabilities that we see in the systems. First, in the surface layer, we have what are called wind-induced Ekman rolls. Like Langmuir cells, they line up with the wind. Ekman rolls, they line up with the surface currents. And they take time, right? Because you have to have the inertial currents kick in. And so they're up there homogenizing, constantly homogenizing that upper layer. When the vertical shear kicks in across the thermocline, the Kelvin-Helmholtz rolls kick in. And they broaden the thermocline. The Ekman rolls scavenge off the top and mix it through the surface layer. Now, the Ekman rolls depend on those steady winds. As soon as those steady winds quit, the Ekman rolls are expected to stop. They're just gone from the simulation. And so then the Kelvin-Helmholtz runs are still there, broadening the thermocline. So the LES simulations say the thermocline should broaden after the wind shift. Our ocean models, the mixing in them, say the thermocline stays thin because the mixing is still intense. And so the next slide shows what the glider says. That very top image there, the red line, shows the peak in the wind changing direction. And as soon as that wind changes direction, the glider says the thermocline is going to broaden. Just like the LES says, not like our models say. So here's a new process that we have to get in our models. Next slide. Okay, those are all Irene, Sandy simulations that we were looking at. And we've had this all set up and we're waiting for a hurricane and none came. And so Craig McLean told us that if the hurricanes aren't coming to you, go to the typhoons. They're bigger and they come more often. So we did. We put one of our gliders on the stratified shelf in the Yellow Sea. Hurricane Soulik comes in. It rapidly cools the shelf waters because it's got the same 2-layer system, and it rapidly de-intensifies. And so we want to start looking at the glider data and how it was fed into the numerical models on a global scale. And so the next slide. The first slide here is a comparison of the glider data with the GOFS 3.1, the whole start of our workflow. And you see the very first ENCODA data simulation window on the left. And the salinity is pretty much uniform, top to bottom, until that glider kicks in and gets the 2-layer salinity value. You know, several days ahead of the hurricane, you see the eye passage on the right and the mixing that occurs during the hurricane. So that's for salinity. The next slide shows the temperature, and this is a very telling slide. On the right-hand side, again, in looking at GOFS in the first assimilation window, you see the glider is getting the 2-layer structure better. And so ENCODA is doing a very good job in this region with very little data of getting that initial essential feature right. But as the hurricane comes over, RU-22 sees about 10 degrees or more of cooling. And the global models are only cooling by about 4 degrees. So in the global models, we're getting the essential ocean features right through the data assimilation. It's helped by the gliders, but the global models don't have the essential ocean processes. That's why we have the regional models, and that's why we're doing things like the LES simulations to figure out what processes need to be in the regional models. So my conclusion slide is next. All right. We've identified these essential ocean features and essential ocean processes that are regionally dependent. So please keep contributing to our census as we put these together. This rapid coevolution, we've documented that with gliders in both the Mid-Atlantic and the Yellow Sea. You've seen those there. This ENCODA glider data assimilation, it's a very valuable start for our TOFS DA and beyond as we move forward. So let's keep using that as we move forward until we're ready to kick in with the new assimilation schemes. We desperately need the OSCEs and OSCs and sensitivities, these impact studies in multiple regions. Gustavo has wonderful templates for how we do it in the Caribbean, but we need them in the Gulf, we need them in the South Atlantic, and we need them in the Mid-Atlantic. And the regional glider experience that we have with our scientists here is just awesome. With all these groups across IUSRAs and CIs and other labs, this is a big problem. We need all these PIs. This is a very collaborative project. I want to continue to encourage those very valuable collaborations. Thank you.
Great. Thank you very much, Scott. Really appreciate it.